Hello everyone, and thank you for joining us for the webinar today. My name is Ben Hutchins and I am part of the marketing team here at InfoWorks. The webinar today will introduce how you can benefit from the power of InfoWorks ICM and Optimizer from Optimatics. As we move through the slides today, if you have any questions, please type them into the question box located in the right corner of your GoToWebinar interface. We have two experts to guide us through the webinar today. Firstly, a warm welcome to Lucy Pocock, Senior Optimization Engineer at Optimatics. After spending 3 years in the UK providing on-the-ground technical support to local utilities, Lucy is now based in Melbourne, providing strategic support for customers in Australia, New Zealand and around the world. As a Senior Optimization Engineer in the Strategic Support team, Lucy works with utilities and their consulting partners on education, training and the application of Optimizer to a range of clean and wastewater applications. She specializes in using Optimizer's functionality to inform growth planning, develop supporting procedures, and facilitate the implementation of resilience methodologies. Joining Lucy, we have Paul Campbell, Solutions Engineer for Storm, Sewer and Flood Solutions at InfoWorks. Paul studied as a mechanical engineer and as part of his degree did a year in the industry, working as a water distribution network modeler. He enjoyed it so much he joined the water industry in 2003 as a wastewater network modeler and has been working as a hydraulic modeling consultant ever since. Paul joined the InfoWorks Solution Engineering team last year, specializing in storm, sewer and flood modeling. So that completes our expert lineup. I'll now hand you over to Paul to take things away. Over to you, Paul.
Thanks very much, Ben. So I'll start with a quick introduction to InfoWorks and InfoWorks ICM. And then hand over to Lucy to talk about the Optimizer software. So InfoWorks is a global country. We've got offices around the world, over 200 employees, a good proportion of which are in staff and research and development to improve the software. And as Ben said, my focus is around storm, sewer and flood, particularly InfoWorks ICM, which is an advanced hydraulic modeling software designed to help water professionals manage storm, sewer and flood systems, and ICM Live, which enables ICM models to be run live. That lets the models run continuously and enables the catchment to be modeled as a digital twin, providing continuous forecasts for operational support. So by that, you might be able to gather that ICM models can be used to help the entire water organization on the drainage side. So they're typically used for planning situations where you'd be interested in long-term projections, development situations where you'll be changing parts of the network, building new properties, river changes, things like that. And that would all typically be done in InfoWorks ICM. That's where the models would be created and developed. But then also we have people like the field crews, and they're interested in immediate action. They're interested in what's going to be flooding, what will happen if something blocks or a pump breaks, and the operations team who are interested in short-term response planning. What do they do if they need to plan some works, if they need to turn off or isolate some part of the drainage network? And they'd primarily be getting those benefits from ICM Live. So in terms of hydraulic modeling, you need to represent a wide range of environments, both the built environment, man-made drainage, and also the natural environment of river systems, overland flow, groundwater and the like. And you need to, in our sense, represent a wide range of flooding sources. So in these images, you can see on the top left there's incapacity during intense rainfall, whereby there's not enough gullies to get water into the drainage system. Down the top right, there's sewer escapes where the sewers themselves don't have enough capacity. On the bottom left, there's surface water flow routing going straight over land and then into a water course. And then on the bottom right, there's the effect of large-scale inundation, the type of flooding which can just sit there for days because there's nowhere for the water to go. So in short, real-world hydraulic systems are complex. There's large variability all across the catchment. Different things need to be represented in sewers, rivers, and overland flows. And the best way to do that, I believe, is with InfoWorks ICM. ICM stands for Integrated Catchment Modeling. So it has the ability to model the complete above and below ground drainage systems all in one place. You see the full picture representing all of the elements in the catchment and how they interact together, most importantly. And InfoWorks ICM uses something called the workgroup environment, which is an incredibly stable database environment simulation engine with 40 years of development behind it. And that allows you to bring in-house engineers and consultants together in a remotely collaborative environment because it allows for multi-user access to the databases. And ICM uses the latest GPU, CPU, and workgroup server technology to produce results faster. So there's lots, as I say, it's 40 years of development. There's lots of built-in tools within the model, within the software to help you build the models more quickly. We integrate with GIS, other data systems. We have tools to automatically calculate head losses, inferred data, just some of the examples on screen there. So really, in ICM, imagination is the only limit. You can improve your models with already existing data. You can use SQL queries to automatically update the database as shown there. Or you can use direct scripting, such as Ruby scripts, to tackle tedious tasks and automate things. And then we have something called ICM Exchange, which lets you automate processes without even needing to open the software. So that could be things like importing, rebuilding, auditing, simulating, or exporting the data. And then once you've got the model built on the simulation side, we represent things very realistically, as you might imagine. Because we have a dynamically coupled 1D, 2D engine. For the 2D meshes, we use terrain-sensitive meshing, meaning the mesh becomes more refined where it's needed. And we can accurately represent any object within the environment, such as buildings, curbs, 1D or 2D rivers, infiltration, anything like that. And we can use that to quantify the flooding across 1D and 2D domains. But what is it that makes the ICM simulations run faster? Firstly, in the 1D model, we have a fully implicit numerical scheme, and that allows for larger time steps, which lets you get reliable results in less iterations. We have the parallel processing, which means you can use the full power of your CPU locally, and you can queue up simulations in series or run them in parallel. And then for the 2D simulations, we have GPU acceleration, where it detects systems for CUDA-enabled graphics cards and uses those CUDA graphics cards to massively increase the performance for the 2D simulations. And then we have remote simulations, whereby you can use the best processor for the job. You don't need to slow down your local computer. You can send those simulations off to any computer on the network with a license to run the simulations. And all of this helps you make sure you're ready for any event as it could happen. Because you can relate your results to the real world with links to photos, links to maps, and representing it as it is in the geographic space. You can use rainfall data from prior or future storm events, either historical flooding or forecast rainfall, or you could use design rainfall events to help plan works. And all of this produces accurate and visually rich results as videos in 1D, 2D, or 3D, as we're showing here. And all of this lets you understand your system at a much deeper level. Because you can assemble the data into a realistic representation of the network and the catchment, The software allows you to monetize the flood risks of various network versions to justify capital improvements. And within the software, you can deploy scenarios to explore the most efficient solutions. And so just as a quick overview, InfoWorks ICM on its own is a fully integrated river, urban drainage and overland flow modeling software to offer holistic hydrological and hydraulic assessments. It facilitates project collaboration and team working through the workgroup environment, and it can evolve onto live modeling. And that's everything you can do with ICM, but the Optimatics Optimizer lets you take things a little bit further, well, a lot further, but I'll let Lucy explain that. So if I can find out where it's taken away my ability to swap presenter, Ben, if you could, there it is. If I hand over to Lucy.
Sure, thanks for that, Paul. I'm just going to share my screen here. Okay, so yeah, thanks for that overview, Paul, of ICM, and thanks for that introduction, Ben. It's great to be here today presenting, expanding on what Paul's introduced on ICM and talking about how we at Optimatics and our software package Optimizer can help you get even more out of your InfoWorks ICM models. So I'm going to talk today about transforming storm, sewer and flood planning with intelligent automation. So we're going to kick off, first off, with a poll. Got a couple of poll questions through the presentation today to get a bit of feedback. So there's a poll open now, and the question is, are you currently evaluating modelling options manually? And by that, you know, are you using your ICM models to test out different strategies and evaluate those manually? So I believe you should be able to vote in your poll. We'll give that a couple of minutes. I see the responses are coming through, and we're at about 80% saying yes, so that's good. We have a captive audience in the right spot for today's presentation. So if we take that a step further and we just consider for a moment the context in which we're making these decisions with our models. So we talk about the traditional planning scope, and by that we mean, you know, using your ICM model as an engineer with your best engineering judgment to come up with solutions to problems you face in your network. So the traditional scope there really focuses on hydraulic performance and cost. So the traditional scope there sort of fails to address, you know, the complex nature of the space in which we need to be making our decisions. So on the right, we've got what we're referring to as the explosion of factors, you know, that are relevant to our decision-making processes today. So along with hydraulic performance and cost, you know, you'll all be aware that we need to be considering things like our budget, risk and resilience, our water quality, and then even beyond sort of those traditional planning metrics, we need to think about political implications of different strategies and how they impact the social and community environment around us. So we really need to be making these decisions in quite a complex space, and just considering hydraulic performance and cost, you know, can be a bit limiting. So with Optimizer, you know, we're helping to expand into that, you know, that multi-objective decision making. So we're going to kick back to another poll. The question here is, do you limit the options based on your engineering judgment to make the analysis manageable? So, you know, you're restricting the number of options and the number of combinations you can consider to be able to feasibly get that assessment done. And we have a pretty overwhelming response on this one. Ben, do you want me to bring up the results, or are you able to flash those? Great, thank you. So we've got 86% saying yes, and 14% are still able to consider all they want to, but a pretty strong amount of you are limiting the number of options based on you know, what's feasible to compute. And so just following on from that, how many scenarios do you normally create for comparison? So I think we've got a bit of a multiple choice here. is it 1, 2 to 3, 4 to 5, kind of getting an idea of how many scenarios you consider. So we'll give people a couple of minutes to equalize. So most people, we've got sort of 45% at the 2 to 3 scenarios and 35% in 4 to 5. So yeah, we're sort of looking, somewhere more than 1, but probably less than 5, and a couple of people are looking at more than that. So that leads really well into what I'm going to talk about next, which is a really high level representation of kind of if we were going to approach a problem manually versus what it looks like if we're using Optimizer. So we can imagine we have a problem in our network. Perhaps we have a certain amount of flooding, and we've predicted that with the expected growth that we're going to have in our network, our existing system is really just not going to be able to meet our required flooding standards. So we've got too much flooding predicted in our network. So we can think about our performance along the y-axis with poor performance, so high flooding being in this high region and really good performance being down here. And we've got a certain level of acceptable flooding that we know we need to hit. So we're currently operating up here somewhere. So if I was using my engineering judgment and my ICM model, I would sit down with the model and, I would make some informed choices, and I would test out 5 different strategies represented here by the orange dots that I'm going to evaluate for performance and see how do they go in terms of flooding. And I can see that 2 don't perform very well. They still have quite high flooding, and 3 of those strategies perform around my acceptable level. So I'm pretty happy with these 3 solutions in terms of performance. So I'll take those forward for costing. And I can see that one is quite a lot cheaper than the other 2. So in terms of what I can feasibly do manually, I'm probably going to accept this plan and take that forward for design. And then maybe I will consider the other implications of that strategy. So now if we think about what this problem would be, what the process would be if we were using Optimizer, we take our ICM model, which is a really important part of this process, but instead of testing out these 5 strategies individually, we're going to tell Optimizer all of the things that we could change in the model. So we're going to say these are all the variables that we could consider changing. And on the other side of that, we're going to say, this is how we want our system to perform. So these are all my performance metrics that I want to hit. And then Optimizer is going to run through many thousands of combinations of those strategies to come up with this green range of points here, what we call our Pareto front. So this is obviously really great and provides really good insight for 2 main reasons. So the first great outcome of this is that, we typically see savings in around 20 to 30% in the optimal solutions versus what we can come up manually, mainly because we can just consider so many more options in Optimizer than what you can test out. But the other thing is that we get a lot more insight into the behavior of our problem. So rather than having discretely tested these 5 solutions, I can see a range of solutions for any given cost. So I can see whatever my budget is, I know that I'm going to be having the best performing solution for what we have available to spend. The other thing that we can do is we can start to ask more interesting questions of our problem. So if we have a certain budget, based on these results, we may say, well, perhaps it's worth spending slightly more to get to this point which performs slightly better. And we can see that, beyond this point, the money we spend is not going to be as efficiently spent because we're not getting much value for money here. The performance is not improving. So we understand a lot more about our problem. We have more confidence in our decision making, and we can really sort of ask more interesting questions of how we want to solve our problems. So just briefly here, we've sort of split out the core Optimatics technologies versus what changes from problem to problem. So on the Optimatics side, we have the computational intelligence. So that's really the link between a computational cluster and your ICM model through the Optimizer interface. And that's that piece at the bottom, the graphical user interface for configuration. The piece in the middle here is the algorithms. So that is basically how we are coming up with those many thousands of strategies and which combinations to try. The algorithms that we use are very efficient and we're, always improving those to become better and faster at solving these problems. On the configurable side, obviously the ICM model and the data, that's an input that we need to bring in. So we rely on an ICM model having been created. The objectives are obviously going to be defined by the user based on the project. And finally, the interventions and the performance criteria. So they'll be specific to our problem. So just got a summary here of the InfoWorks products that we integrate with. So obviously on the collection side, we integrate with ICM, and on the distribution side, we integrate with WS Pro. And I've got a very simplified slide here of sort of how that connection works. But basically on your local machine, you'll have your ICM panel, your window as you're used to, and you'll also have an Optimizer user interface. And on your local machine, we use ICM Exchange, and that's something Paul mentioned at the start. So Exchange is really the key here to connecting the ICM model into the Optimizer. So that's how information is passed back and forth. So on your local machine, you're able to load in your model, set up your configuration within the Optimizer interface and push data back and forth as required. So when you've set up your formulation in Optimizer, through an API, we can connect to a bank of solvers that both have the ICM engine and ICM Exchange. So on a dedicated computational cluster, that's going to run through the required evaluations. So that's where those thousands of evaluations occur. The summary of that is our Pareto point, and we're going to get that back onto our local machine, and we're able to interrogate that and take certain strategies that we like back into ICM, where we can use the full software again to interrogate that solution. So I've just got a few slides here to give you an idea of the Optimizer interface. So we've got a map display in the middle where you've got your ICM model that's been imported. On the right-hand side, we have our plan editor, and this is where you can view each column here represents alternative strategies. And we can see the decision outcomes down the bottom, and you can see a summary of their performance. So this is how you can interact with different strategies. Another panel here showing just the data browser, where we can view the model elements and set up various parts of our formulation. And then on the right, we just have an example of a Pareto that's been downloaded from the cloud. Our red points here are our optimal, and we're able to interrogate those further here. So to kind of get our heads around how we would set up a problem for Optimizer, so you'd be used to the process of tackling it just with your ICM model. But if we want to frame a problem in terms of an optimization, these are the five questions we always need to ask ourselves. And so these are always relevant. And the first one is what's the question? What's the problem? It's obviously very simple, but it's very important to focus the optimization and to define your objective functions for this particular problem. So next we need to think about the input data. So one of those is your hydraulic model, obviously, your associated cost data, any additional asset information. So we may need to bring in different data sources into Optimizer to support that. The third piece is really important. It's really important to understand that Optimizer does not create options out of thin air. It does not suggest a pipe where there is no pipe currently. You must have all of your options defined in your ICM model, and then Optimizer is going to play with different variants. So it can choose to have a pipe or not have a pipe, and it can choose to size that pipe appropriately. So it's going to play with the elements that are there, but you do need to define the options to begin with. The fourth one is defining the desired performance. So that's all about, those ICM hydraulic results. So anything that you would normally go and check, like the flooding or the freeboard or the surcharge, they all form part of your design criteria, which tells Optimizer a good solution versus a bad solution. And finally, we can think about what scenarios are going to be relevant. So I'll talk about scenario analysis in part of our case study in a moment, but that's really important, where once you've got your Optimizer formulation set up, applying that formulation across a range of scenarios is really easy. So that's a great benefit. You're able to kind of ask some more interesting questions, then gives you a bit more capacity to kind of ask more what-if questions across those different scenarios. So a slide here this is by no means a complete list, but I've just listed out some examples of the functionality and the specific components that we work with in Optimizer and ICM. So the decisions are things that we change. So, these will probably be quite expected. We're changing conduits and pumps and storages. So this is things that we can vary in the ICM model. So as well as the infrastructure of the model, we can also change, controls and the operational philosophy of the model. So, anything you would change in your ICM model could form part of a decision in Optimizer. Then in terms of design criteria, I've just listed some of the ones that we have here, just your typical results that you'd be wanting to look at that are going to be important to you when you're solving a problem. In terms of objectives, these are some common objectives that people will optimize for, obviously cost and performance, and then maybe social benefit or, some of those other factors. If we can quantify those, they can also form part of your optimization. And finally, the costs and data is obviously required to be brought in. We need to think about the range of pipe sizes available, the range of pump curves, all our costs need to all be brought in. So that's kind of the end of the introduction to Optimizer. I'm going to take 10 or 15 minutes here to take through a case study. So this is an example of a collection system network planning optimization. The problem statement here, or the question, was how do we plan for growth and a changing system, which is a problem that, is very commonly encountered. I'm sure a lot of you grapple with this in various ways. So for this particular problem, the inputs we brought in, obviously we had an ICM model, we had our cost data for the new assets, and we had a number of scenarios. The decisions we were considering, we were looking at pipe alignment and sizing, storage location and sizing, and various green infrastructure options. So this project, it was important to think about the traditional conveyance and storage upgrades, but then also looking at what could we do with green infrastructure to solve this flooding problem. The criteria here, we were looking at obviously flooding, surcharge and freeboard, and the overflow or discharge in the system. So overall, we're minimising cost and maximising level of service. So a moment here to talk about some of the what-if questions that we asked with Optimizer. So for this problem particularly, one of the questions was, what level of service should we target? So, should we be aiming for a 10, a 20, or a 30-year level of protection? And that was one thing that we explored in this problem, and I'll show you a bit more on that in a moment. So other what-if questions we can ask is, what scenarios are we planning for? Is it existing or future? Is there cost sensitivity we should be considering? Are there impacts of climate change that we may need to plan for? And finally, what type of strategy should we consider? So as I mentioned, conveyance storage, SUDs, are there other strategies we should be considering? So here we're going to walk through an example of the results for this problem. So what I'm showing here is three Paretos from three separate optimizations that have been layered on top of each other in Excel and just extracted here at a high level just for review. So in blue, we can see the results from our 10-year optimization. In orange, we can see our 20-year, and in green, we can see our 30-year. So these are three different hydraulic models that we optimized with the same decisions and with the same criteria. So just take a moment to kind of think about the different results that we're showing here. So across the x-axis, we're looking at increasing cost of implementation, and across the y, we're looking at increasing hydraulic problems. So we have more flooding the higher we go here. So as I mentioned, each of our curves is representing a cost-benefit trade-off, where each point is a unique combination of strategies there. The circles represent our starting point, so they're all obviously at zero cost, but they have reasonably high levels of flooding. So that's where we started from in each of the 10, 20 and 30 years. And the triangles here represent the cheapest plan that solves the flooding. And there's a couple of points of interest here. So it's important here with Optimizer, it's part of the benefit that we don't just get one solution, we get a range of solutions. So if we think back to our acceptable level of flooding line in the hypothetical problem above, there's a horizontal line here defining anything above is more flooding than we're happy to accept. So we're actually only interested in these solutions that meet that minimum level of flood protection. So all of these solutions we actually weren't interested in exploring. And obviously this is the ideal point on the plot that we would love to get to, but we never will, where we spend no money and have no problems. And you can see how the Pareto is, pushing towards that point, but it obviously has to either spend money or sacrifice performance to try and get there. So now if we just think back to what we have here in our results, so if we take the 10-year scenario, we can see that all these blue points up to this point don't solve our flooding, but these ones here, when we zoom in, we actually can see more of a vertical distinction, kind of teasing out some of that performance improvement. And we obviously want to interrogate these strategies to see what we're coming up with. And what's really good about this kind of multi-scenario optimization is here we were able to say, well, this is how much more it's going to cost to get you to a 20-year level of protection. And this is how much it's going to cost to get you to a 30-year. So they can make an informed decision on how much flood protection can we afford and what makes sense. So diving into those Pareto points a little bit more, so in terms of the individual strategies, we want to ask ourselves a couple of questions. So we obviously want to find out, what do we build and where? So we want to delve into, the specific alternatives that Optimizer's coming up with. And we also want to understand the costs and the performance measures a bit more. So, why are these solutions the best solutions? Why can I be confident in these? So this is one example of how we can dive into those Pareto points a bit more. So here each bar represents one optimal strategy, and we've just ordered these in terms of total cost, and then we've broken them out in terms of the contribution of cost from different intervention strategies. So we can see our conveyance in terms of pipes, we can see our storage in terms of tanks in yellow, and then finally our green infrastructure options in light blue here. And one thing to point out before we jump to the cheapest solution is that if we remember on our Pareto, certain solutions didn't actually solve the flooding. So all of these plans here don't perform well enough for us to consider them. So we're really only interested in these plans and ones that cost more than that. So a couple of things that we can notice here from our results is that the conveyance and tank costs actually flatline. You know, once we start spending a certain amount, the pipes don't get upsized further. The storages don't get any bigger. We just see the cost starts increasing through the green infrastructure options. And we can also see that at the higher cost end, that's where we have quite significant SUDS implementation. We can see some small implementations here at some of the cheaper ones, but they don't really start showing up until we're at this level of spend. So there's a few things obviously we can draw from this. One is that if you want to spend, you know, the lowest amount possible, you're probably not going to be wanting to look at SUDS, but obviously green infrastructure has a lot of other benefits. So in this case, there were other drivers where they wanted to consider where they should be putting green infrastructure. So it wasn't just about the cheapest solution. We really wanted to see, okay, if we are going to invest in green solutions along with our, you know, pipe and storage solution, where should we put that? So to kind of help give us confidence in if we are going to invest, where they should go, this is another example of output that you could extract from the Pareto. So what we're seeing here is a heat map of our subcatchments, and the likelihood that a certain subcatchment has been selected for a green infrastructure intervention is what is being coloured. So the red catchments here are ones that are repeatedly chosen in the optimal solutions and being highlighted for green infrastructure. So this kind of assessment is helpful to say, look, SUDS, you know, in this case may not be the cheapest solution, but if we do want to invest in some, we know that this is going to be the best place for it. We're going to get the best value for money by installing that here. So we have our second to last poll question now, which is, do you account for social, environmental and or carbon impacts as part of your optioneering processes? I've also got one for all of the above. So we're seeing a few things come through here. Interesting. So we'll give a few seconds for those to be collected. Got two kind of pretty equal coming up, and we can see, all right, so environmental being an important consideration, and then actually a lot of people choosing all of the above. So a pretty good spread where, you know, we are needing to consider these, you know, additional objectives, especially environmental impacts. So if we think back to when I compared the traditional planning process, thinking about cost and performance, obviously very important for our decision making. But, you know, we also want to be thinking about natural capital, social benefit, maybe risk, water quality, so kind of a broader context to our decision making. And here I've got some examples of, you know, some conceptual three-dimensional optimizations. So previously we were looking at cost and performance, and it's very easy to simply add a third objective, and maybe we're quantifying the additional benefits of SUDS, or, you know, the environmental benefit of including green infrastructure. So anything that we can quantify along with our interventions, we can include in our optimization. And obviously the great thing about that is, rather than having to kind of consider it as an afterthought, maybe with a short list of options, we can kind of have that part of the the optimization process along with cost and performance, so we can kind of be making our decision and choosing our strategies really with a consideration to all of our objectives. So we have one final poll question here before I hand back over to wrap up, but would you like more information? And I'll just take this moment to say thanks very much for your time. Thanks InfoWorks for setting this up, and I'll hand back over to Ben to wrap things up for us.
Brilliant. Thank you very much, Lucy and Paul, for introducing us to the power of InfoWorks ICM and Optimizer today. If you asked a question, we promise to get in contact with you with an answer. I'll be updating you with a recording of this webinar next week and providing you with links to more of our upcoming webinars. Please do visit our website for more information about our virtual training courses. And please take a moment to complete the quick survey that follows this webinar to receive a certificate that you can use for proof of professional development. Lastly, a big thank you for joining us today, and we hope you have a great day, everyone.